Let us start our class. I'm sorry I'm a bit late because I was slightly sick. We'll continue our discussion on the strain analysis itself. We have started our discussion over strain analysis. First, we know that stress is proportional to strain as per Hooke's law. Stress is proportional to strain. Next, strain can be of two types, longitudinal and lateral. Means if the leg, due to the effect of external load, due to the effect of external load, external load, the concerned prismatic part elongates contracts longitudinally and contracts elongates laterally. Now, what happens here? There is a specific relation between longitudinal and lateral elongation. That is given by, there is a specific ratio called Poisson's ratio, which is given as nu or nu. Nu is equal to lateral deformation, lateral contraction or deformation, say contraction or lateral strain. Let us block it like this. It is not deformation, but is strain itself. Lateral strain divided by longitudinal strain. Condition is it should obey Hooke's law. That is, it should be loaded within elastic limit. Okay, but it is strain, lateral strain by longitudinal strain. It is the relation between strain between strains, not the relation between deformation. Which means the strain means deformation per unit length is equal to defined as strain. You know, lateral or longitudinal. Let us go back to the discussion. This was the basics of all this strain analysis. What we have seen here, this is the relation just I have told you. This is the constant, which is known as mu. So values of mu works between 0.25 to 0.35 almost of the material itself. Now there exists two-dimensional strain. Just 1 second, please. There exists two-dimensional strain. There two normal stresses acting. One is sigma 1, like this, say along x-axis, and along sigma 2 and y-axis. The net strain in direction sigma 1 will be sigma 1 divided by E, the longitudinal strain, minus mu multiplied by sigma 2 by E, that is lateral strain, lateral longitudinal. Same is the case with respect of epsilon 2 or epsilon 1 itself. Now, just 1 second. Next is comes three-dimensional stress system, where we are using normal stresses on sigma 1, sigma 2, and sigma 3, as shown here. Sigma 1 along x-axis, say sigma 2 along z-axis, and sigma 3 along y-axis, etc. So the net strain in direction of sigma 1 is given by sigma 1 by E. Here we are considering the longitudinal strain, and nu into sigma 2 by E, and nu into sigma 3 by E is the lateral strain along the direction of sigma 1. Strain in a similar way, epsilon 2, or the strain in the direction of sigma 2, and epsilon 3, strain in the direction of sigma 3 is given by this equation like this. Here comes another formation. The body is subject to three mutually perpendicular stresses. Their volume will also change, and which is referred to as dilatation or dilation of material itself. Now, volumetric strain is defined as the ratio of strain, the increase in volume in a body divided by the original volume itself. So here we are first calculating the initial volume as A, B, C, where A and B and C as the dimension of the say our top-typic prismatic volume cube, and final volume will A plus epsilon 1, A plus A epsilon 1, B plus B epsilon 1, C plus C epsilon 1, which is equal to ABC 1 plus epsilon 1 multiplied by 1 plus epsilon 2 multiplied by 1 plus epsilon 3 itself. So volumetric strain, the increase in volume divided by the original volume. So this is the final volume, and if you subtract the initial volume from it, you will get the increase in volume. Thus, we have made like this: final volume minus initial volume divided by the initial volume itself. And this, when we are this ABC will cancel from both numerator and denominator, and the relation will result in 1 plus epsilon 1, 1 plus epsilon 2 into 1 plus epsilon 3 minus 1, or which is more or less equal to epsilon 1 plus epsilon 2 plus epsilon 3, while neglecting the extremely small item like epsilon 1, epsilon 2, into epsilon 1 multiplied by epsilon 3, epsilon 3, epsilon 1, the epsilon 1 multiplied by epsilon 2 plus epsilon 3 minus into epsilon 3 minus 1. So these products are very small quantities are neglected here. What we are doing, so the volumetric strain is the summation of the direction of the strain along the sigma 1, along sigma 2, and along sigma 3 stresses itself. Thus, we also can have the differentiation, volumetric strain by differentiation. So where delta V will be BC into delta A plus CA into delta dV plus AB into DC. If we divide both sides by V, then dV by V, that is epsilon Y, dA by A, that is epsilon 1, plus dV by V, that is equal to epsilon 2, plus DC by C, that is equal to epsilon 3 itself. Now, these terms of the stresses in the volumetric strain expressed by the term, you see, epsilon 1, epsilon 2, epsilon 3. So, dV by V becomes delta P by V. We are expressing in terms of sigma here. We put the value of respective strains, epsilon 1, epsilon 2, and epsilon 3, in terms of sigma 1, sigma 2, and sigma 3, which will look like this. After simplification, it will become sigma 1 plus sigma 2 plus sigma 3 multiplied by 1 minus 2 into nu divided by the coefficient of elongation, that is constant of proportionality E itself. Now, we have gone through one problem here, which we have discussed. What is given in this problem, which we have discussed in the last class, that is the volume of the steel bar is what is the percentage change in the volume of the steel bar, whose dimension is as 20 millimeter diameter and 600 millimeter length, with the when a tensile stress 180 MPa is applied along its longitudinal axis. Given the your constant of proportionality, and nu is equal to 205 GPa, and nu, that is the Poisson's ratio, given as 0.3. Now, whereas the dimension of the bar is given here, diameter and length, so you can have the volume pi by 4 d squared into length itself 6000 into pi millimeter cube. The change in the volume, as per our last required definition here, which is here, V volume multiplied by sigma into 1 minus 2 into nu divided by E. Volume we have just calculated is 60,000 into pi, where sigma is given as 180 MPa only in the additional axis. This is given here, multiplied by 1 minus 2 into nu, which is given as 0.3. So, and that divided by the constant of proportionality E, 205 into 10 to the power 3, as it is given in GPa multiplied by GPa or gigapascal. It should be converted to megapascal, which is given kg per square millimeter. So it is, we are multiplying it by 1000 or 10 to the power 3, and after simplification we are getting the change in volume equal to 66.2 millimeter cube. So percentage change in volume will be the change in volume by the original volume multiplied by 100 will be equal to 0.035 or 3.5% only. Next, let us go to another problem that is new to us. Let us go through the problem one after another. That will be clear for you to understand the matter. Here we are getting in the one example number 34, the tangential or hoop stress and longitudinal stress in the plates of a cylindrical boiler. In the plates of a cylindrical boiler of 2.2 millimeter diameter and 3.5 in length are given as 90 MPa and 45 MPa respectively. So hoop stress or longitudinal stress no, sorry. Hoop stress or tangential stress is given as 90 MPa and longitudinal stress is given as 45 MPa. But question is, what is hoop stress? What is longitudinal stress? Let us explain first again. Say if we have a cylinder of shape like this, which has certain length, it has certain length, certain thickness, and certain radius and certain thickness. It is a length here, say L, from this direction. It has certain radius, say here, from here to here, that is radius, and it has certain thickness here about the surface itself like this. And if it is closed in both the ends here, this end as well as this end, and is subjected to some internal force by filling it up with some pressurized fluid, if it is filled up by fluids under pressure, more than the surrounding atmospheric pressure, then what happens? it is subjected to stresses along the length, longitudinal stress, longitudinal stress means longitudinal stress is stress along the length, longitudinal stress along the length, radial stress along this direction, radial stress along the radius, and tangential stress like this, tangential stress, real, or it is also called properly known as hoop stress along the tangent. Okay. So here in our given problem, what we have witnessed here, what there is no radial stress is given, but there is longitudinal stresses, hoop stress is given, or the tangential stress is given, and longitudinal stress is given. And we know the dimensions of the cylindrical boiler, which is of 2.2 meter diameter and 3.5 meter in length, and we know the hoop stress, we know the Young's modulus, and we know the Poisson's ratio here, and we are supposed to calculate the increase in internal capacity itself, means increase in volume. So as we know the dimensions, diameter and length, will have the volume of the boiler itself, boiler drum, and pi by 4 into 2.2 square multiplied by 3.5 is equal to 2.235 mu pi multiplied by pi to the power I m to the power q, means cubic meter. The now next is that we have to determine the volumetric strength. Thus, we have to determine the composite stresses due to the steam in the internal surface of the cylinder as sigma z is equal to 0, means there is no radial stress, no radial stress. Sigma x, or the hoop stress or tangential stress is given as sigma c divided by E minus gamma sigma L by E. What is sigma c? Sigma c is the hoop stress given. Hoop stress given, and sigma L is the longitudinal stress given. Along the tangential strain, when you are calculating the tangential strain, epsilon x, tangential strain, then we are using the tangential stress sigma c divided by E, which is the predominant stress, and predominant strain minus mu multiplied by the longitudinal strain divided by E, and it is across the as it is acting normal to the circumferential stress itself. And we put in the value 1 by E, 90 is given as 90 AP is given as value of sigma c multiplied by 0.3, which is given as the value of the Poisson's ratio nu multiplied by 45, which is given as the value of the longitudinal stress sigma. So after simplification, we will have 76.5 divided by E as the value of the tangential or hoop strain, and longitudinal strain or epsilon y is a longitudinal strain, that is epsilon v sigma L by E minus gamma sigma c by c, but we are saying around the longitudinal length, the longitudinal stress is acting, and due to the effect of the tangential stress along in normal to the longitudinal axis, it is creating lateral strain line. This is given by nu by E multiplied by the lateral stress sigma c or hook stress sigma c itself. Again, we are putting the value of sigma L and nu and sigma c here, and we are getting the value. After substitution, we will get the longitudinal stress as 18 divided by E itself. The diameter of the boiler is directly proportional to its circumference itself. So thus F psi C also is the diametral strength along two perpendicular radius itself. So the volumetric strength is given as F psi Y, F psi X, and F psi X. So what is given here? The diametral strength or tangential strength stroke hook strength or circumferential strength of hook strain is acting in two mutually perpendicular directions as F psi X in X and Y direction, and longitudinal strength is acting in Y direction. So thus we are using F psi X twice here and only F psi Y only once here. That is longitudinal stress given at 18 divided by E plus 76.5 into divided by E plus again 76.5 divided by E.
Hello, sir.
Hello.
Hello. So we have the next class from 9:50.
Just one second. Yes. What was that again? Hello.
Sir, we have the class from 9:50.
Yes, I know you have the class. I have started this late. Okay. So
yes, sir.
I think I will take another 5 minutes to forward this problem. Okay.
Okay, sir.
5 to 10 minutes, then you can join. I will talk with your respective teacher. No problem. Now, so we have we put the value of sigma F psi Y divided by E plus F psi X plus F psi X itself. And if we simplify again, we'll have the volumetric strain as equal to, by putting the value of E itself, we'll have the volumetric strain 834.1 multiplied by 10 to the power strain. Now, as the strain is a ratio, change in volume can be multiplied by directly in cubic field. What is the change in volume? The strain multiplied by the original volume itself. Strain is given here, we have just calculated this one, and volume is already, you have calculated 4.2355. So that is equal to 0.011 into 0.011098 m to the power cube. That is equal to change in volume will be 0.0010098 into m to the power cube, or that is multiplied by, if we multiply it by 1000, it will convert it into liter. One liter is 1000 cc itself. So we are converting it into liter by multiplying it by 1000, so it will become 11.098 or liter or cc itself. Just I am quickly going to another problem that will be not very lengthy. It is a lengthy problem. Let us start for a few minutes. Steel bar. What is given here? Steel bar is 35 millimeter. into 35 millimeter in section. This cross section area is 35 multiplied by 35, and 100 millimeter is the length in accord is acting upon by a tensile rod of tensile load of say 180 kilonewton along the longitudinal axis and 400 kilonewton and 300 kilonewton along the axis of lateral surface itself. So what is steel? This is the dimension. This is the cube itself, or steel bar, not cube but the steel bar. While this cross-sectional dimension is 35, it is 35 and length 100, and it is a tensile load 118 kilonewton, which is here shown here along its longitudinal axis. It is 180 kilonewton. It is also already written as tensile, but it is shown as compressive load. That is, it will be the compressive load itself. And as another, and 400 and 300 newton along the axis of the lateral surface. Means lateral surface, these are the surface, one lateral surface, and this is the one lateral surface. So 1 over it is 400 kilonewton, and another is 300 kilonewton. So we have three mutually perpendicular forces, which is shown as compressive in a figure. That's 120 longitudinally and 400 and 300 in lateral surface on laterally itself. So what we know the steel bar is the size of the steel bar, its cross-sectional dimensional length, and we know what are the different loads acting over it. And we know the Young's modulus as 205 GPa multiplied by 10 to the power 3 MPa, and Poisson's ratio of mu into 0.3. Now, what we have to find the change in the dimension, change in the volume, and axial load to produce some same longitudinal strain as above. Now, sigma 1, sigma 2, sigma 3 is the stresses. So, what will be a sigma 1 when the load is given 180? Means this load is acting over this cross section itself. So, dimension is 35 into 35. So, it's 180 multiplied by 1000 to convert it into Newton, divided by 35 into 35 is equal to 146.9 megapascal or kg per millimeter square, or Newton per millimeter square. Similarly, this 400 kilonewton is acting over this particular surface whose size is 35 multiplied by 100. So 400 divided by 100 into 35, 114.3 megapascal or Newton per millimeter square, and sigma 3, which is the load acting over this surface, which has dimensions again same 35 multiplied by 100 itself. So 400 divided by 400 into 35 is equal to 100, 114.3 megapascal itself, divided by sigma 3, and sigma 3 is 300, is 300 kilonewton acting over it, but dimension is 10, 85.10 megapascal itself. So we got sigma 1, sigma 2, sigma 3 itself. The length longitudinal strain, strain in longitudinal direction is delta L. The length, where L is supposed to be here itself, which is brought here, multiplied which L by E multiplied L1, sigma 1 minus mu into sigma 2 minus mu into sigma 3. We have calculated sigma 1, sigma 2, and sigma 3, and we know nu. We put them together, and length is given as 100, and E is given as 200 to the power 3. So longitudinal direction deflection, longitudinal deflection, or change in length is 0.0435. In the 400 kilonewton load direction, same is the case. We are using the length as 35, and we using the respective value of the stresses sigma 2, sigma 1, sigma 3. What is sigma 2? 114.3 minus 0.3 multiplied by 146.9 is equal to 0.3 into 85.7 is equal to 0.0076 millimeter itself, divided by 200. 200 is the value of P, and length is given as 35. In the direction of 300 kilonewton, the length is again 35, and E remains same, and sigma 3 into nu into sigma 1, nu into sigma 2 is all given sigma 3 is put here, the sigma 3, we put the value of sigma 1 here as here, and value of sigma 2 as here, is equal to 0.00125 millimeter itself. So we have got the change in length in three direction, in mutual perpendicular direction. So we have to add this change in length with the original length 100, original length 35, original length 35 with the respective change in length. One was 0.4239, another was 0.0076, another was 0.00125. And we subtract the original volume, which is 100 into 35 into 35, and so, and we got the change in volume as 82.92 millimeter cube. Or directly, the change in volume, we can safely use this relation directly, and we'll get the same change in volume here. The longitudinal axis load, axial load, the stress is the longitudinal stress to have the strain. So what we'll have, we calculate the strain, longitudinal strain here already 0.04239 divided by the length, which is given as 100. So strain is given as which is equal to the strain divided by Young's modulus, or then strain will be 86.9 megapascal itself. Or the longitudinal load, if we multiply the cross-sectional area, 86.9 into 35 into 35, or 106.452 kilonewton itself, which is what we calculate here, the equivalent weight, equivalent stress as well as equivalent length, that is equivalent stress and load actually it will be like this. What we are calculating is stress and load equivalent to the strain equal to point equal to longitudinal strain to the null strain 0.04239. Okay, that is the question, and this is the answer of this particular question itself. Okay, thanks for your patience hearing. Thanks for staying up to the class to this moment. I'm stopping this class here.